All right, welcome everyone. Welcome back to the channel. In today's video, we'll be diving into the fundamental data types for the CompTIA Tech Plus FC0 U71 exam. This is a key topic for exam objective 1.2, so let's make sure you're prepared. So, our agenda will be introductions. We're going to talk about the concepts, and then we're going to go through some definitions and examples. And then we'll follow it up with some sample questions and answers. So we'll work through the actual math behind it. And then we'll cover some final tips and some takeaways. So for our first part here, it's important to understand that in 1.2, we're going to talk about 4 different things. We're going to talk about binary, decimal, hexadecimal, and octal. So let's break down each one. Our first one is binary. Binary means that it's a base 2. So that stands for only 2 symbols. So 0 and 1. It's like an on and off state, true or false type state. So it's the language of computers. Computers use binary because that's what they operate with. So if we see something like the binary number 1010, it would be represented by the decimal number 10. And the way that we would do that is we know that we have 4 positions here. We have 4 positions, 1010. So we would take 1 and then times it by 2 to the third, all right, because we know that it's a base 2 and we're trying to count down to 0. And then we would do 0 times 2 squared. And then we would do 1 times 2 to the first power. And then we would do 0, 2 to the 0 power. So basically, we're always trying to count down the powers here. So if we work out the math, it would be 8 plus 0 plus 2 plus 0, so it would equal 10. So that's how we would convert binary to decimal. All right, for our next one, we're going to talk about decimal, base 10. Fairly easy to understand because the decimal system is using your 10 symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your only possibilities here. So it's a standard numbering system that most people use in everyday life. It's based on our natural counting with 10 fingers. However, keep in mind that we're starting with 0. So if we have the decimal number 123 is just 123. So again, if we run through the math, counting down based on 3 positions, we'd start with the power of 2, and then we do the power of 1 and the power of 0. So it'd be 1 times 10 squared plus 2 times 10 to the first power plus 3 times 10 to the 0 power. So 100 plus 20 plus 3, so it equals 123. We're going through this math on this one so you understand how we get there. Again, has to do with it being a base 10. All right, next up, hexadecimal. Hexadecimal is where it gets a little confusing, but don't get too hung up on the details. Hexadecimal is a base 16, so the hexadecimal system uses 16 symbols. It uses the same as decimal, so 0 through 9 for the first 10 values, and then A through F for the next 6 values. So A, alpha, is equal to 10, B, Bravo is equal to 11, C, Charlie is equal to 12, D, Delta is equal to 13, E, Echo is equal to 14, F, Foxtrot is equal to 15. So you would have 0 through 15, which is 16 symbols altogether. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 16 different symbols. Hexadecimal is often used in computing because it's more compact than binary and easier for humans to read. It's particularly useful, though, in programming and color codes, like in web design. So that's the reason why this exists. And you'll see how much shorter it is to represent things. So for the hexadecimal number 1A, it would represent the decimal number 26. So we would take 1 times 16 to the first power plus 10, which is the representative of A, times 16 to the 0 power. So again, we're doing two positions and we're counting down to 0 with the powers. So 16 plus 10 equals 26. That's how we get there. All right. Last but not least is octal, base 8. Octal is not very common today, but the octal system uses 8 symbols, 0 through 7. So just like decimal, but we don't have 0 through 9. So same concept. Octal was more commonly used in older computing systems, particularly for simplified binary data. Each octal digital corresponds to 3 binary digits, making its conversion easier. So if we take the octal number 17, it represents the decimal number 15. So again, we got two positions here. We do 1 times 8 to the first power because we have 8 possibilities, plus 7 to the 8 0 power. So it equals 8 plus 7, which equals 15. All right, I know it can be a little confusing, so let's look at the tables. The tables put it into perspective. So if we look at the tables and we take a look at decimal, 0 is going to be 0 across the board. So this is a 4-digit binary conversion table. If we look at 1, 1 in 4-digit binary is represented by 0001. It's represented by 1 in hexadecimal. It's represented by 1 in octal. So as we go through this, as you recall, we had 8 positions with octal. It's pretty straightforward. 7 is going to be 7 is going to be 7. Okay, makes sense. But where it gets a little confusing is we get higher than that. When we get higher than that, it does get a little more confusing, hence the reason why we need to convert. Now, if you look at hexadecimal, you'll see the 16 different options. Hopefully this also makes a little more sense. So 0 through 9 and then A through F. So if we look at decimal, 0 through 15. So we have 16 possibilities there. Now, where the real savings comes in is when we look at 8-bit binary digits. 8-bit binary is what your symbols, your characters on your keyboard represent. So just imagine if you had to always type in 8 bits of binary to represent a character. It would be very cumbersome. And that's why some of these numerical representations can really save a lot of space, especially when we talk about hexadecimal. It really makes it a lot more compact. So again, when we look at this, pretty straightforward, 0 through 7 again, it's the same type of concept except for we're adding in the 0 up front to represent 8-bit binary digits. All right, let's look at a couple of actual samples here though. What do these samples look like? So some sample questions, something that you could definitely see on the Tech Plus exam. A technician receives a task to convert the hexadecimal number 1F to its equivalent in binary. Given that each hexadecimal digit represents 4 binary digits, which binary number is the correct representation? So if we know 1 in hexadecimal equals 1 in decimal, and F in hexadecimal equals 15 in decimal, we can take the 1F and we know that we're going to start with the 1. We know that F in hexadecimal is equal to 15. So we would take the 1, times it by the 16th power to the first, plus 15 times the 16th power to the 0. So 16 plus 15 equals 31. Okay, makes sense. So when we look at the conversion down here, 0001, 1111 is the binary representation. All right, another example. What number does the binary representation of 1010 correspond to in decimal? Again, we have 1010. We're going to start with binary. We know it's binary. We want to convert it to decimal, so we know that we're going to be using base 2. So we take our 1 times 2 to the third, 0 times 2 to the second, 1 times 2 to the first, plus 0, 2 to the 0. So it becomes 8 plus 0 plus 2 plus 0, and it's going to equal 10. So 1010 corresponds to 10 in decimal. All right, next one. Which of the following is a way to express numerical values using a base of 16? Well, we learned that binary is a base 2, decimal is a base 10, hexadecimal is a base 16, and octal is a base 8. So the correct answer is hexadecimal here. This is a pretty frequent question here. They'll ask something like this, and then they'll just change it to be either base 2, base 10, base 16, base 8. So pretty straightforward, no math, no need to do anything. So that is definitely a nice, welcome question to receive. And then last but not least, a technician is debugging a piece of software and needs to convert an error code from decimal to octal format. The error code is 10 in decimal. What is the corresponding value in octal? This is pretty easy when we need to convert from decimal to octal. So we would convert the decimal number 10 to octal by doing 10 divided by 8. So that would be 1 with the remainder 2. So it'd be 10 in decimal is equal to 12 in octal. 12 in octal. So 1 remainder 2 equals 12 in octal. Pretty straightforward when we get these two. So don't be intimidated by these. These are welcome questions as well. All right, so in summary, all these systems are just different ways to represent numbers. Don't let it intimidate you. There's no reason to memorize the tables. We just need to understand how to convert with the common systems. So binary to decimal, decimal to octal, octal to decimal, that sort of thing. Just like the questions that we reviewed, those are very similar to what you would actually see on the exam. So again, thanks for watching. If you found this video helpful, make sure to hit the like button and subscribe for more CompTIA exam prep videos. Don't forget to drop a comment if you have any questions, comments, concerns. Happy to respond to those.